The sweet sound of a phaser. We've all heard this classic effect on countless recordings, but have you ever wondered how a phaser works? If you have some basic electronics knowledge, stick around and I'll show you. It all starts with this simple circuit, an all-pass filter. All-pass filters are an interesting thing because they pass everything, all the frequencies, which I know is not very interesting. What they do to phase, though, is pretty cool. Let's add an input signal and make an inverted copy of it 180 degrees out of phase for the other input. And we'll add a ghost of our original wave just as a reference to see what this filter is doing. So at low frequencies, the capacitor has a high reactance, and all the current goes through the resistor. That's the non-inverted wave, so there's no change at the output. At high frequencies, the capacitor has a low reactance, acting like a short. So now none of the current goes through the resistor. Only the inverted wave gets through, so the output is 180 degrees out of phase. At frequencies in between the low and high extremes, the phase is somewhere in between 0 and 180. So now we have a circuit that can change the phase of a signal depending on the frequency. This is all well and good, but how are we supposed to make the inverted version of the input? Sounds like a job for an op-amp. The op-amp version of the all-pass filter uses the inverting and non-inverting inputs to deal with our problem here. The gain is set to 1 with RF and RI. In the case of this particular setup, the low frequencies all go to the inverting input, and the high frequencies go to the non-inverting input. Now, as the frequencies sweep from low to high, the phase changes from minus 180 degrees to 0 degrees, with a sweet spot at the center frequency where the phase is minus 90. Now you're probably wondering, where's all the math? Well, there it is. It's our old friend, the FC formula. So when you really want to know which frequency will be 90 degrees out of phase, use this. 90 degrees doesn't mean much yet, but it will in a few minutes. Now, let's blend the all-pass filter's output with the original input. As you can probably guess, this doesn't do much except to put the low frequencies out of phase so they cancel out. So we haven't really done much except to take a roundabout route to making an overly complicated high-pass filter. But we know that this particular filter is working its magic with phase instead of just cutting down the amplitude of certain frequencies. So if we put a second all-pass filter in series with the first one, some real voodoo starts to happen. Remember how the sweet spot was a certain frequency that gets put 90 degrees out of phase? Well, now it gets put 90 more degrees out of phase. That makes a full 180, which results in complete cancellation when you blend it with the input. Only at that frequency though. The low frequencies, which used to be 180 degrees out of phase, are now 360 degrees out, which means nothing. It's just like being 0 degrees out of phase. The high frequencies, which used to be 0 degrees out, have gotten another 0 degree shift, and you guessed it, they're still 0 degrees out. So the overall response curve now looks like this, which unfortunately sounds a little boring. Okay, so far we've built an op-amp based all-pass filter that does some magic. We've hooked two of them together to get some voodoo. Let's bring in some wizardry. What if we could move the center frequency? What's the center frequency again? Right, the FC formula. Looking at this, we can see that the frequency will change if we modify either R1 or C1. Resistors are the easiest thing to change, so let's tackle that. Change it out for a potentiometer, and there we go. Wait, you're not going to be able to turn that potentiometer. You're going to be busy rocking out. We need a way to automate this process. Enter the low frequency oscillator. I'm not going to go into the details of how an LFO works, but the idea here is that it puts out its own waveform, a slow one. We're going to use that changing voltage to control the resistance of R1. Okay, now we're getting into full-on sorcery. If we put some JFET transistors in parallel with R1, we can have the LFO send its changing voltage to the gate of the JFETs. As the voltage at the gate changes, so does the resistance from the top to the bottom of the JFET. Now, without any interaction from us, the LFO cranks out its slow waveform, changing the resistance of R1, and so the center frequency of the all-pass filter moves around, all while we're busy rocking out. Thanks for listening.